So in this video, I'm going to go over the principles of air source heat pumps. These are very commonly used HVAC appliances. A lot of the industry is moving in this direction, especially in the residential scale, although there are some other technologies. But the heat pump in general, but the air source heat pump in particular, are becoming increasingly popular. So how does this work? This is the exterior unit of what's called a split system, which we won't get into too much detail. But the thing about these air source heat pumps, or just a heat pump, is that they use electricity, but a couple of things are really important here. So since they use electricity, they're not a combustion appliance. Okay, so there's no combustion here. There's nothing's being burned. It's just using electricity. But also very important, it's not a space heater. Okay, so space heaters use electricity to generate heat, but they convert electricity directly to heat. Whereas a heat pump, what it actually does is it takes electricity and it drives the refrigeration cycle, which I went over in another video. So it's different even in heating mode, which this thing will heat and cool. In heating mode, it's not doing the same thing as a space heater. It's not taking, there's no, the primary method is not by using electric heating coils. Most of the heating comes from the refrigeration cycle. And one of the beauties of this is that you can actually heat and cool with the same unit. And so it's called a heat pump because what it actually does, all it does is takes heat from one location and sort of dumps it in another location. And here are two examples of schematics for heat pumps. So here's your exterior unit, so that would be this thing right here. Here's an exterior unit right here. So this is called a split system because it's split. So you have your exterior unit and then your interior indoor coil, or sometimes called a air handler. Anyway, so this is a split system. And so here's how this works. This thing, all of the electricity is used by the exterior unit. And so if you are in heating mode, so let's say it's a colder time of year, in heating mode, what it's actually doing is this exterior unit, okay, is actually pulling heat from outside of the exterior unit here. And so, and that's using the refrigeration cycle. So you're pulling heat from outside. Okay, so heat's getting pulled in. Okay, even if it's cold outside, using the refrigeration cycle on latent heat of vaporization, is you can actually pull heat from the outside. And in this case, if it's in heating mode, it's actually evaporating. So it's using evaporation inside the unit. Okay, so the evaporation of the refrigerant is what actually pulls the heat in. And so what it does is then it actually goes through here. Okay, so your refrigerant line, and then what it's doing actually in this case is it's releasing the heat into the air inside the duct, and then it's going to circulate through the duct, and then the heat is going to come out here. Okay, and so same principle here. If this is heating mode, it's pulling heat from the outside air, and then that refrigerant is going through your refrigerant line, and then it's going into, in this case, this is a hybrid system. So this also has, this is actually a natural gas line. So this is a natural gas. So you can use this natural gas as supplemental heat, and that's often used if it gets really, really cold. The heat pump can't quite handle it and pull enough heat from the outside air to operate properly. So you'll have a natural gas backup at times. But anyway, this if it's pulling heat from the outside, and it's going to release heat then in this case into the ductwork here, and that's going to take the heat out to the rest of the building. And this is your return, so the cooler air is being pulled in from the rest of the building, and then that air is being heated again, and the cycle continues. And so the nice, one of the nice things about the heat pump is that this is just a closed loop. And so if you look at this one over here, you're going to have the heat's released into, so it's heat's going out here in the ductwork, and that refrigerant just going to come back and go in here, and then it's going to pull more heat in, okay, and then it's going to go back, and then it's going to release its heat, come back. Okay, so it's a cycle. It's a heat pump. Like I said, it moves heat around, basically. So the same thing here, your refrigerant line, it dumps your heat in here in the lower image, and then it comes back out, and then it pulls more heat in, and then it releases it, okay? So it's a cycle. And as I said, one of the beauties of this is that you can reverse this. So a heat pump can be used for cooling. So in cooling mode, just use this one for cooling mode. So in cooling mode, it's just the reverse of that. Okay, so cooling mode, what you actually do is you're pulling heat, heat's coming, okay, so you're pulling heat here, and then it cools, so basically it pulls heat from the air around here, which cools down the air, and then the cool air is circulated through here, and it goes out here. Remember, it's grabbed all that heat through evaporation, and then in this case, it's actually dumping the heat outside of the building. Okay, so then there's a fan in here that's going to blow and sort of facilitate that heat release, and then it cools down, comes back in here, pulls more heat in, blows more cold air out, and of course you have the circulation here, comes back out, releases the heat, and so forth. Okay, so that is the beauty of the heat pump, is that you can reverse this process. Okay, so you buy one unit, and it literally reverses the flow. And so that's the beauty of the heat pump. All of this uses electricity to move heat around. It does not use, generally speaking, does not use electricity to run your coils. Okay, so good question. How efficient is this? Why do we use a heat pump? As it turns out, they're very efficient. So if you ask the question, how efficient is it? It's actually not exactly the right question. What you really want to know is how efficient is it at cooling and how efficient is it at heating. And so to measure the effective, it's not technically called an efficiency because you're not converting electricity directly to heat. So efficiency is a little bit of a misnomer, but for our purposes, we'll just call it the efficiency. So the measure of how effective it is, how efficient it is called, for cooling mode, is called SEER, Seasonal Energy Efficiency Ratio. Okay. So the formula is pretty straightforward. As long as you can get these numbers, it's really easy to calculate. So this is our seasonal energy efficiency ratio. So it's seasonal. So it's throughout the entire season how much heat is removed, okay, in BTUs. All right. So the whole season, if you can measure how many BTUs of heat, remember it's pulling heat from the building and dumping it outside. In cooling mode. So how many BTUs of heat is removed during the season, and then you divide that by the electricity used throughout the season, and this is important, it's in watt hours, not kilowatt hours. All right, so that's you'll almost always hear this refers to as SEER. So you'll see a SEER, a 14 SEER, 15 SEER, whatever. So the EPA has efficiency standards called Energy Star standards, okay? And so they tell you you have to have a minimum rated efficiency in order to get the Energy Star label, which means effectively they're relatively efficient. So in order to get an Energy Star rating, you need to have at least a SEER of 14. You can get up to 27. I've seen them a little higher than that, but that is your sort of minimum level of efficiency for the EPA to say, okay, this is a pretty efficient unit. Okay, so that's your SEER, so that's for cooling. So the one last thing with this is for the seasonal, right? So SEER is seasonal. You can also do the EER, the energy efficiency ratio, which is just under given conditions, okay? So not over the season. We won't use that as much. We'll more often in this course refer to SEER. Okay, so how efficient is it at heating? It's very, very similar in terms of the formula, but it's a totally different term. Heating Season Performance Factor, Hspf, is what you normally refer this hear this referred to as. And so it's almost the same exact equation, except it's the heat added during the season in BTUs, and then the electricity used in watt hours. So remember, SEER is how many BTUs of heat is removed or are removed. This one is how much heat is added. So again, you're pulling heat from outside and you're dumping it inside the building. So Energy Star rating for Hspf is actually a little bit lower. in the U.S. in general, in the mid latitude, toward the northern parts of the country, it gets pretty cold. So it turns out it's not as efficient at heating in general. And so the highest is around 13. I've seen them a little higher than that. Okay, so HSPF, how much heat is added during the season, and divided by the electricity used in watt hours. And just like we had the EER for the sort of under specific set of conditions, the cooling effective efficiency, we have what's called the HPF, which is the energy used under given conditions, not over the entire season. Okay, so let's look at a quick sample calculation. So I have a heat pump. Remove 70 MMBTUs of heat over the cooling season and uses 4,800 kilowatt hours. What's the SEER that year? So assume you have all these measurements. So what's the SEER? So I need my heat removed in BTUs and I need my energy used in watt hours. So my energy used is going to be, now you got to be careful here because this is in kilowatt hours. All right, and so we need to convert this, right? So we have 1 kilowatt hour is 1,000 watt hours. So this is going to be 4,800,000 watt hours. And now we have everything we need because we know that an MMBTU is just equal to 70 times 10 to the 6th BTU, right? So my SEER is just going to be dividing these two. So 70 times 10 to the 6th BTU, and you divide that by 4.8 times 10 to the 6th watt hours, okay? And if we do that, we get 14. We'll just round it to the 6th, 14.6, and technically this is BTU per watt hour, but you won't really use the unit. You just call it equals 14.6 SEER is normally what you'll say here. Whoops. Okay, and so this is a good time to do a little, a reality check. Is 14.6 SEER, that's reasonable, right? So Energy Star is about 14, so that's a good number. If we get like a SEER of 2, we probably did something wrong. If we get a SEER of 50, we certainly did something wrong. So let's do a HSPF calculation real quick, okay? So if your heat pump has an HSPF of 5 and uses 1,000 kilowatt hours, how many BTUs do you get out of the heat pump? So let's do this real quick. And in this case, we do a little bit of algebra. So we have HSPF. We'll just call it heat added over electricity used. Okay, so because in this case we have the HSPF, we have the electricity used, so we need to get heat added. So if you do some rearrangement, you're going to multiply times electricity used on both sides. Sorry. Right? So your heat added then formula equals your electricity used times your HSPF. So electricity used is 1, remember we'll convert this to watt hours, so it's 1 million watt hours times my HSPF of 5. So my heating added is going to be 5 million yes, sorry, that should be BTUs here. Nope, that's not right. Sorry about that. So that's 5 times 10 to the 6 BTU, which is just 5 BTU. Okay, so with some simple algebraic rearrangement, you can do in the other direction as well.